Hello, I'm recording another video about some new ideas on the connection between tableau proof systems and optimal beta reduction. This is Aaron Stump, and in my first video about this recently, I was talking about the idea that this proof method called tableau could possibly lead to a new approach to optimal beta reduction. And so I'm assuming my viewers here know something a little bit about optimal beta reduction, maybe more than I do, but maybe don't know so much about tableau. And so last time we talked about tableau proof system for classical propositional logic, and that's a great starting place to understand the basic idea of tableau. But we're going to go through a series of steps to try to get to another notation for optimal beta reduction. And those steps, the first one of those steps is we need to go from classical logic to intuitionistic logic. And the reason for that is that we're going to try to be able to view tableau proofs as some kind of graphical notation for lambda calculus. And so since at least typed lambda calculus usually is considered to correspond by the Curry-Howard isomorphism to intuitionistic logic, we need to understand tableau for intuitionistic logic. I think we'll be able to see that these ideas will pretty easily extend to untyped lambda calculus as well. But we don't want to allow, I think, the kind of effects you get when you look at Curry-Howard for classical logic. You get certain kind of control operators, which, while possibly cool and interesting to use, let's not pursue those here. So we're just trying to get something that lets us do essentially untyped lambda calculus, optimal beta reduction for untyped lambda calculus, and we're going through the route of tableau. And so just to kind of review my proposed roadmap of what we're going to try to do. So you have tableau for intuitionistic propositional logic. We're going to try to do that now in a short time before I meet with somebody here in my office. And then from there, we need to switch to sort of graphical. I'm sorry to say graphical tableau. Maybe that's not the right word. We're trying to look for direct connection or something like that. Tableau, as we saw last time, and we can review this time, the tableau proofs allow you to add certain formulas at the end of a branch. The tableau are certain kinds of trees, and you can add formulas to the end of a branch based on finding a formula way up earlier in the branch. So there isn't really a direct connection that you can see in the tableau itself from the stuff you put at the end of a branch to sort of its immediate origin or ancestor. And so we want to change that. And so we're going to try to have, I have no idea if this is something you could find in the literature on tableau. I'm not an expert on tableau. But we're going to try to have a different notation for tableau where the connections are more explicit. And let's see, so we need to do that in order to get closer to a graphical notation for lambda calculus with sharing. And then we need to consider cuts. Normally tableau are for representing cut-free proofs. And so you normally aren't interested in representing cuts. But we need that to write down lambda terms that aren't just in normal form. It's very nice to have a fancy graphical notation for normal form lambda terms, but we actually want to compute, and so we don't want just normal forms, we want arbitrary terms. And so for that, we're going to have, on the logical side, we're going to have cuts. So we're going to add cuts added to the tableau. And let's see, is there anything else we have to do at that point? Oh yeah, and then of course, then we need cut elimination, which is going to correspond to the reduction process. And we need to do this with sharing, and in particular, we will need to introduce certain kinds of duplicator nodes similar to what you would have seen in standard presentation of optimal beta reduction, but we'll see it arises a bit differently here. How differently? Does it really solve any great problems or anything? I can't tell you right now. I can just tell you that this seems to be a different path, quite a different path to arriving at a similar but possibly somewhat different version at the end. And so I'm hoping that this will actually yield some benefits. Anyhow, this is a pretty long roadmap. It's going to take a while to get through all that. And so the first thing to do today, though, is to go back up to step 2. We need to transition from classical tableau to intuitionistic tableau. And it's actually pretty easy to do, which is great to know. And there's a couple different ways to do it. But the right starting point for this, though, the way that I think looks most promising is, Tableau based on Kripke semantics. Now, you might not be familiar with Kripke semantics, so I want to tell you a little bit about that first. If you are, you could try to skip ahead somehow past this bit, past what's Kripke semantics. So Kripke semantics, so in other words, as we know, the intuitionistic logic, the validities of intuitionistic logic are a subset of the classical validities. In other words, intuitionistic logic is just a restriction of classical logic that doesn't let you do certain kinds of deductions. And in particular, ones that, from a logical perspective, are non-constructive. And from a computational perspective, well, these sort of non-constructive deductions are somewhat weird from a computational perspective, and we're not going to go into that. But so anyhow, we're going to have tableaux that are more restricted than the classical tableau in order to get fewer validities, which is what we need if we're going to have intuitionistic logic or any proper fragment of classical logic. So anyway, intuitionistic logic is let's say as a presented by proof system, axioms and rules, can be proved let's see, I guess the right way to say is is sound and complete. We're talking about propositional intuitionistic logic here. Is sound and complete with respect to Kripke semantics, with the formulas that are valid under Kripke semantics, validity under Kripke semantics. So in other words, over on the syntactic side, if you can prove, so here let's write single turnstile to mean prove. You've got some rules for proving formulas, and if you can prove formula, maybe I'll just continue to use capital T for these, anticipating the Curry-Howard isomorphism where those will be types. If you can prove T, you can prove T if and only if T is semantically valid, where the notion of semantics is given by this Kripke semantics. Kripke semantics was proposed by Saul Kripke, a really great logician and philosopher who had a number of just amazing, interesting ideas. I actually had the opportunity to see him give a presentation. Goodness, it was 20 years ago now, or something like that, when I was a grad student. And the presentation was a little crazy. He had a cart of books that he wanted photocopies of, and he was trying to distribute them. And it was like, I had no idea what he was trying to talk about, but I did get to see the great man in person, which was exciting. Anyway, so Saul Kripke proposed this semantics. I can't tell you about the history of this really more than just to tell you the technicalities. So the idea is, and works for modal logic, and intuitionistic logic turns out to be actually a form of modal logic as well, which is interesting. The implication is the modal operator, or the modality is sort of hidden in the implication. And anyway, the semantics, the basic idea of the semantics is that we're thinking of truth in a world, or sort of like a snapshot of time, or a possible world, or there are different analogies that make sense. And we think about that truth can evolve in a certain way. So if you draw a world here, let's say, let's say this is today down here, and up here is sort of tomorrow. But let's say these represent some alternative possibilities, because these are graphs that can branch. So tomorrow number 1 and tomorrow number 2. Different future alternatives that could take place. And so we get this branching graph. And the idea with the Kripke semantics for intuitionistic logic is that if a formula T is true at a world, like say now or today, it has to remain true in the future. It can't switch to being false. Going forward in this graph of sort of possible alternative futures, if you want to use that metaphor, the formula has to remain true in all possible futures. So once it's true, it's got to stay true. Okay, but under Kripke semantics, it is allowed that if a formula is false out of world, it could, but does not have to. It could eventually become true. World, it is allowed to become true. It doesn't have to, but it could become true. In the future, okay? And this sort of seems weird a little bit, but if you think about it as something like knowledge, like say we're saying, if T is false at a world, maybe that really means we believe it to be false, or maybe it means we don't know that it's true. And so our knowledge can evolve as we go into the future, things that we didn't know to be true now, or maybe it could be provability or something like that. Things I don't know how to prove today, maybe I can figure out how to prove tomorrow. Something like that. So our positive knowledge can increase going into the future. That's a good sort of, from a sort of social history or sort of cultural perspective, that's a good, I don't know if you want to call it enlightenment or progressive kind of viewpoint. Things are just, our knowledge is just getting richer and richer as we go forward. It's all sunshine in that way. Not a philosophical perspective I actually share personally, but that does does jive with that. Anyway, so so if things are false, they could become true. And so the way we set this up is sort of technically is that we have an idea of a Kripke frame. So a Kripke frame is a set W of worlds. Okay, these are all these possible alternatives we have out there, together with basically with a reachability sort of graph. So with a binary relation, if you want to do this set theoretically, you think about having a binary relation, and let's just denote it using some kind of symbol here that sort of looks like an ordering symbol on W. Let's see, actually, I think I want to double check my definition here because there's some other components one needs here, but I don't quite remember if we put those in the Kripke frame or somewhere else. Okay, I'm looking at the Mintz book on intuitionistic logic, and he doesn't really say. He just kind of lumps all this stuff together. No, sorry, I had it right. He separates them. Okay, so now so that's the frame. It's just kind of the structure of these worlds. It's like what worlds do you have, and which ones are connected to which. Now there's something that's required here. This relation has to be reflexive and transitive. You can think about the future time kind of version of this semantics, and then it would sort of make sense. It's kind of, right now is considered a sort of degenerate case of the future, and if something is in the future of a future world of mine, then it's a future world of mine. So we have transitivity, okay? And by the way, these are the conditions that you also have for the modal logic S4, if you're curious about this sort of thing. Has the same conditions on the frame. And in fact, modal logic S4 is related in some ways to intuitionistic logic. And you can find lots of papers out there that talk about some of these connections and interrelations, and even exploring Curry-Howard for S4, I think I've seen. So anyhow, but we're just looking at this. And let's see. So anyway, we have this Kripke frame that gives us sort of the structure of our world. Now we need to say what's true and false at the various places in the worlds. So we say and I'll follow what Mintz has here in A Short Introduction to Intuitionistic Logic, his book. So a Kripke model is a Kripke frame. So you get sort of the structure of your universe, together with a valuation function that's going to tell you what's true and false. Let me see, how does he formalize this? Yeah, okay. A valuation function V. I mean, we're dealing with propositional logic, so we need to say which atomic formulas, your P, Q's, and R's, your propositional variables, which ones of those are true and false at the various worlds. So this valuation function takes in an atomic formula, and it also takes in a world, and it gives you a Boolean value. Is it true or false there? Okay, so so you could ask, is propositional variable P at world W, is that true or false? So this is in true, false. And it's just telling you the truth value for that atomic formula P. Okay, and there's a requirement on these valuation functions that corresponds to what I was speaking about informally at the beginning. The truth is supposed to grow. So if things are true now, they have to stay true. That's really the only requirement you need to make. So you say such that for all atoms, I could write this way, and for all worlds W, we could just say, if V, P, and all worlds W and all worlds W prime, such that W prime is in the future from W. Now I'm sort of writing a mix of meta-level logical notation in English, so maybe I'll just write a fully meta-level logical notation or mathematical notation. So this has to imply, VPW needs to imply VPW prime. So atomic formulas that are true now need to be true in the future. And notice that this formula doesn't say anything about the ones that are false. So the ones that are false could, and I guess depending on how you want to look at this, maybe I should have said, if this equals true, this is a Boolean valued function I'm saying, so I should speak about what value it has, I guess, and then I say it needs to be true in the future. Okay, so okay, so that's the basic idea, and we could give some examples graphically. Like you could say, let's see, if I'm smart, I give you one that's actually useful to know, like a counter model to P or not P. Let's see. Anyway, okay, so let's say that here at this world, let's say, so this is, let's say this is world W1 and this is W2, and let's say that V says that P at W1 is false, but P at W2 is true, let's say. So that's a good example where something was false in the past but becomes true. And yeah, this is actually a counter model to P or not P if I didn't screw up, and we'll see that when we say briefly what the semantics are now. So now the Kripke semantics for intuitionistic logic formulas is the following. So we're going to say, given some Kripke frame and together with evaluation V, and let's just denote this by some kind of K, calligraphic K or something like that. So given K and W, which is some world, little w's in big W, some world, we're going to say we're going to define when is a formula T true at that world of that Kripke model. Okay, and so here's the definition. It's recursive definition, recursive on the formula. So if you have an atomic formula, then you just ask the formula, you just ask the evaluation. Is this thing true or false? Okay, so here I've written this meta-level notation to define this. So this underlined part here with the saying, when is the atomic formula true at world W of this Kripke model K? And it's true if and only if the valuation there says it's true. So the valuation says it's false, then we're going to say it's semantically false. Okay, so that's that. We have a couple really easy cases, and I'm going to rush a little bit because I got a meeting in like 3 minutes. So T1 or T2, this is just devolves into the meta level or. So if this one is true, or if T1 is true, or if T2 is true, then we're going to return Boolean true. And is the same kind of way. So all this is not very exciting or interesting. The exciting case is implication. But let me just quickly write out these easy cases. I'm writing capital AND here to just kind of emphasize it's the meta level conjunction. Okay. What about false? Because we want to include a symbol for false. So if we have the logical formula false, well, that's false. So in other words, the logical formula false is always false in whatever world you're in. Now here's the cool case, which is implication. All right. So T1 implies T2. When is that true? That is true if for all future worlds, so for all W prime that are in the future from W, and remember that it could include W itself because this relation is reflexive. So for all future worlds, in that you look in that future world, and in that future world, T1 is being true needs to imply T2 is being true. So in other words, the semantics of implication works just like it sort of does classically, but it has to be true for all future worlds. And so if we come back quickly here, because I really got to stop in just a minute. So if we look at P or not P in this example I gave above, so P or, now we're going to say P implies false. Then this thing is, so if that were to be a theorem, it would have to be true in all Kripke structures, but it's not true, I believe, unless I messed up, in world 1 of the Kripke structure above. P or not P, and not P is usually defined as P implies false in intuitionistic logic. It's not true at that world. And why is that? Because for it to be true, so K, W1, P or not P, by the definition of the semantics for or, this is that either we have to have P true at that world, and I defined the semantics up there, so the model said, here I'll just draw it again real quick. So here P becomes true, this is W2, but down here it's not true, so I could just not write it to sort of indicate by its absence that it's false. So at world 1, P is not true, and otherwise, for the negation to be true, we need to know that for all future worlds that are in the future from W1, that in those future worlds, this W prime, if P is true, then false, because then we need to know false is true. Just a second. I just need 1 second. Okay, so let me finish up here real quick. Okay, so that it needs to imply false, because we said false is always, the false formula is always false. So in other words, it has to not be the case that P is true. And so if you kind of look through this then, so the first thing is false. So that's not going to contribute anything. Or we need to know that in worlds W1, P is false. That's true. That's good. It is. But what about in world W2? So at KW2, we need P to be false, but it's not. So this whole thing is false. Okay, so there you go. That's an example as counter model to P or not P, and that's an example of using the Kripke semantics. Okay, I need to stop now as I'm talking to somebody, so I'll pick this up again, who knows, hopefully pretty soon, and we'll see what the tableau system is for intuitionistic propositional logic based on Kripke semantics.